section 2.6 is about polynomial and rational inequalities. I've got an example here of a polynomial inequality on the right side of the board, and I've got a related problem on the left side of the board that's similar to what we were doing earlier in this chapter. Here we're asked to graph the polynomial function x cubed minus 4x. So that would be graphing in the xy plane, because remember f of x is just a fancy name for our y values. Okay. Now here, I've got the same polynomial, but instead of being able to graph it, being asked to graph it, I'm being asked what values of x make this inequality true. Anytime you're asked to solve an equation or an inequality in one variable, you're asked what values of that variable make that thing true. Now the connection here is that this is what's giving me my y values over here. So essentially this inequality is saying what values of x make the y values on this graph be less than 0. Nice thing about comparing to 0 is that being less than 0 simply means being negative. So when we're comparing to 0 with an inequality, we can just look at the sign of things. Okay. All right, so let me just remind you how we would do this graphing, and then we'll see that some of the work that we do there is going to be the exact same work we need to do to answer this question here. When we're graphing a polynomial, I want to have it written in factored form. In this case, I can see that I can factor out a greatest common factor of x. And that's really nice because then the second factor is not only quadratic, it's a difference of 2 squares. So that factors as x times x minus 2 times x plus 2. So with that, I get my 3 zeros of this polynomial would be 0, which makes that factor 0, 2, and negative 2. That gives me the location of my x-intercept. So I'll have an x-intercept at negative 2, 0, at 0, 0, and at 2, 0. Now in this case, because we passed through the origin, we've also plotted the y-intercept as well. Okay, so then I need to know how to connect the dots, and one method we had for doing that was to create a number line, and we could just mark off these zeros, negative 2, 0, and 2, because since polynomials are continuous, the zeros, which are the x values of the x-intercept, give me the only locations at which the function could change sign. Because if it's going to change from positive to negative, or from negative to positive, it would have to pass through the x-axis. Can't jump over it because polynomials are continuous. So the only places it can cross through the axis are where there's a point on the axis, and that occurs at these 3 numbers. So we've seen these numbers divide the number line up into 1, 2, 3, 4 subintervals, and we know that our function has a consistent sign on each of those subintervals. And so we can check. I'm going to just list each factor, x, x minus 2, x plus 2, calculate the sign of each of those, and then see how they would combine to give me the overall sign of f. And usually I just pick a test number. So I need a number smaller than negative 2. Let's try negative 3. Okay. So negative 3 would be negative. Negative 3 minus 2 would be negative. Negative 3 plus 2 would be negative. And 3 negatives are going to multiply together to give me a negative. So my function is negative to the left of negative 2. I could also have determined that by looking at the end behavior of this, because it's dominated by a lead term of x cubed. As we go really far off to the left, this is going to do the same thing that x cubed does when we go far to the left, and that's going off to negative infinity. All right, between negative 2 and 0, I can pick a text number. I'm going to pick negative 1. Negative 1 is, of course, negative. Negative 1 minus 2 is negative, but negative 1 plus 2 would be positive. 2 negatives and a positive are going to give me a positive. So you'll notice we change sign here. Another way I could get that is by observing that negative 2 corresponds to this factor of x plus 2 that only occurs once in the factored form. So because the multiplicity of this 0 is 1, which is odd, we actually cross the axis there. So I've got several ways that I can figure this out. I'm just going to keep going with the test numbers. If I plugged in 1, that's positive. 1 minus 2 is negative. 1 plus 2 is positive. Two positives and a negative make my function negative. To the right of 2, let's try 3. 3 is positive. 3 minus 2 is positive. 3 plus 2 is positive. The product of three positive factors is going to give me something positive. And so now I'd be able to sketch this polynomial. It starts out negative. We cross the axis and are positive for a bit. Then we come back. We cross the axis and are negative for a bit. And then we go off to infinity. So my graph looks roughly like that. And of course, without calculus or a lot of trial and error in plotting points, we don't know the exact location of the max and the min value that we have there. Okay, excellent. So that's what we just did. A lot of that work is exactly what we're going to need here, because I wanted to know when this was less than 0. Less than 0 simply means negative. I was looking for what intervals of x values are going to make this function negative. So I could create exactly the same number line and mark off -2, 0, and 2. Again, the zeros of a polynomial are the only place where it could change sign. Okay. Now, when I'm working with this inequality, I like to, once I've marked off those numbers, indicate whether they're going to be points that are included in my solution or not, because my solution is going to be a bunch of x values, the x values that make that inequality true. These points will not be included, so I'm going to put open circles around them. The reason they're not included is because at these points, this expression is equal to 0. It is not less than 0. If this was less than or equal to, I would put solid points there. Since it's a strict less than, I'm going to put open circles there. But then I can do the same test for the number line, and we got negative, positive, negative, positive. I'm just going to write these results in since we just did that work. Looking at this, I wanted the places where it was negative. I'm just going to shade that so that I've got a picture. And then I'm going to state my answer. So my answer, and I'm going to give this in interval notation. As a general rule, I'm going to ask you to give things in interval notation. The only exception to that would be if you have something where there's just a single number that's a solution. And when we encounter that, I'll show you how to deal with that scenario. But let's in general give our answers in interval notation, and that's going to be consistent with what the book does. So this interval would be -infinity to -2, union this interval, which would go from 0 to 2. Okay. The connection that this has with this is if I look over here, where was my function negative? Where it was below the x-axis, and that was to the left of -2 and between 0 and 2, which is what we've said right here. So the difference is that here I was looking for a graph in the xy plane. Here I was just asking a question about some x values. Okay? But this creating a number line, finding the places where things could change sign, and testing the resulting intervals, that work is the same for both sorts of problems.